Welcome to session 4, that is subject microcontroller, and the subject code is 18EC46. So in the previous three sessions, so what you have seen is what is microcontroller and what is the architecture of the microcontroller, and today we will see what is regarding the pin numbers and what is each function of the each pin. Okay, so now how it is segregated or separated these sessions is, so initially, so we have seen what do you mean by microcontroller. So basically it is IC, so which will be used in embedded system to control or to develop to control the operations. Okay, so then, so after knowing what it the microcontroller, then what is inside of IC, so what it consists of, so which are the blocks, for example CPU, RAM, ROM, timer circuits, control, all those things, control circuit, all those things. Okay, so that we have seen the block diagram, and inside the again the block diagram, what internal circuit, what it consists of, registers, register map, all those things we have seen. So once we know the architecture of the microcontroller, then we need to know once, because it is in the form of IC. Okay, so what are the in outs, we call as what are the inputs and outputs of the microcontroller, how to interface. So how to interface we'll see in the later session. Okay, so now what are the inputs and outputs of the microcontroller and what is the functions of that. Okay, so that we will see in the today's session. Okay, so the same thing, the contents of today's session, so it will be uh, the 8051 pin diagram and IO port functions, the same pin, the pin functions of each pin, and RISC and CISC architectures, Harvard and Van Neumann architecture. Okay, so these are the three topics, so what we will see. And now the pin diagram. So the pin diagram of 8051, it looks like this. So totally the 8051 microcontroller, it has 40 pins. Okay, it will start from 1 and it is end with a 40, and the direction will go like 1 to 20 is like this, and 21 to 40. Okay, so always it is 8051 whatever microcontrollers are there, so 20 is the ground and 40 is a VCC. So that is a fixed 20 ground and 40 is a VCC. And again, as we know in the architecture, 8051 has the 4 ports. Okay, so this is port 1, and this is port 2, and it is port 0, and this one is port 3. Okay, so each port has 8 pins. Okay, port 0, port 1, port 2 and port 3. So now the whatever ports are there, each one we can access with individual pin, like port 1.0, 1.1, okay, 1.7, like this. Okay, so port 0 is multiplexed, both address and data can be used in the, as a means port 0 will act as either address bus or data bus. Okay, so based on the control signal, so you'll see later. And port 2 will act as address bus and normal IO, and port 3 will act as IO, and it will is a multifunctional, means the port 3 the normal IO, and also it will do some controlling signals. It has some control signals with respect to interrupts and serial communication and timers. Okay, so that is the job of port 3. Okay, and rest of that 3 pins, that is EA, that is external access, and ALE and PSEN. So these 3 are control pins, and pin number 18 and 19 are that is clock related pins. Okay, that is crystal oscillator pins, those two, and ground and VCC. So except this, all are the ports, all pins are shared with the ports. Okay, so this is one of the diagram, pin diagram, and this is one more pin diagram. So here what are the pins, what you have seen now. So the same thing, it is extension, means for example if it is AD, what is AD, address bar data. Okay, and as it is somewhat short, means the text is very small, so I have taken that and this both diagrams, address and data here, and external enable or external access, address latch enable, program store enable, and here this RxD means receive data, transmit data, interrupt 0 and 1, timer 0 and 1, write and read stops. Okay, these all things we can see the names here. Okay, the same 40 pins. So now after seeing all these things, okay, so we will go on to the pin number 1 to 40 one by one, and what is the job of that. Okay, so VCC means here we will give the 5 volts power supply. Okay, so we'll see one by one. Let us start with the first 1 to 8 pins. Okay, so 1 to 8 pins we call as port 1. Okay, so we call as the port 1. So port 1 is a which will served or configured as a input or output. So each 8 pins, so whatever 1 to 8 pins, or we can call as 0 to 7 pins, so all each pin we can configure as either input or output. Okay, so because of that each pin we call as a the bidirectional. Okay, so that we call as internally pulled up. Pulled up means it will be connected to the through the resistor, it will be connected to the VCC. Okay, so based on our power supply. Okay, so now the port 1, it is now, it doesn't have any other function, so except the normal input and output. So this port 1 doesn't do any other multifunctioning. Okay, so that is the meaning of that. So now the next one, reset. If you come to the pin number 9, so that is a reset. So reset is a basically the reset signal is required for every system, every embedded system. It is required. Even the desktop computers also will have the reset button. So why it is required is, suppose for example if the desktop computer while working, suppose if it got hanged, okay, if it got hanged or something is not working, it's stuck. Okay, so then once we press the reset button, again it will start booting and again it will start. Okay, so similarly basically the reset signal disables the microcontrollers and clears all the contents of the register. Means almost all, most of the registers will be cleared in the sense, if something in the previous operation or previously if it is any values are set in the registers, so that will be made 0. Okay, once the reset is there, and we call as reset is active high. Okay, so active high means the meaning is like this. Suppose if you take RST, reset is active high, so 010, if we give the signal like this, so reset is active during this duration. Okay, so this we call as a active high, means during high. Okay, when the signal is high, at that time it will reset the microcontroller. Okay, so that we call as active high. Once it becomes low, again it will start the normal operation, means the microcontroller will start the operation. Okay, the next one, pin number 10 to 7, 10 to 17, that is port 3. So port 3, as we know, it can serve as normal input output, and also it will do some multifunctional. So this port 3 is a multifunctional port, so it will do the functions like interrupts, so timers, controls, okay, the serial communications, all those things. Okay, so the same thing we can see pin by pin one by one. So pin number 10 is a received. Okay, receiver pin means, for example, if it is a microcontroller and if it is any external device like ADC or whatever it is, okay, so receiver is, it will receive the serial signal, it will receive sorry, it will receive the serial data from the external device. Okay, external device, it may be anything. From the external device it will receive, so it will be given to the RxD. Similarly, TXD means it will send the data serially, okay, to the external device. So serial in the sense, so per clock 1 bit it will be sent, means for example, or at a time 1 bit will be sent, so that we call as serial. Okay, similarly we have pin number 12, that is external interrupt 0 input. For example, that's what, if the microcontroller is like this, so they have interrupt pins. Okay, interrupts will be coming from the outside. Okay, so what is the interrupt? So interrupt is basically a signal, either it is active low or active high based on the bar. So suppose if it is interrupt bar, then it is active low. Okay, if bar is not there, then it is active high. So interrupt low in the sense, if the signal is coming like this, okay, let us take these are active low signals. If the pulse is coming like this, then the microcontroller will understand that there is a interrupt active, means interrupt has come for this particular pin. Okay, so now there are two interrupts it is taking, external interrupts, interrupt 0 and interrupt 1. Okay, so whenever the interrupt comes, okay, so this particular basically the interrupt is nothing but, so microcontroller is doing some work. So whenever interrupt comes, okay, if the interrupt comes, what the microcontroller should do, so that will be written in some program, okay, that we call as ISR, interrupt service routine. Okay, so when interrupt comes, it needs to stop this normal function and it needs to jump to here, it needs to serve again, it should come back. Okay, so again whether it should handle these interrupts or not, so that will be controlled in the interrupt enable signals and interrupt enable register and interrupt priority register. Based on that, this will be served. Okay, and next is, okay, the pin number 14, counters. Okay, the timer clock input. Okay, if something means, for example, if this pin, if some pulses are coming, okay, some signal is coming on the T0. Okay, this is the input of microcontroller, some signal is coming, so we need to count how many pulses have come. Okay, or suppose if it is coming like this, okay, how many events has occurred, these all things we can count. Okay, so that is a pulses we can count, so that signals we can receive on the T0 and T1. And these are normal, means the basic read write functions. Okay, suppose if you want to communicate with external device, okay, whether if you want to write means we need to send a write signal, read means we need to, I want to read means we need to activate the pin number 17. Okay, so as I said, if it is read bar, then it is active low, and if bar is not there, then it is active high. So if you want to read, if it is active high, the microcontroller will send a function like this, signal like this. Okay, similarly for read. Okay, so these are the control signals will the port 3 will act as when we are communicating with the external world. If there is no if you are not using these signals, so the port 3 will normally act as a normal input and output. Okay, then next one, pin number 18 and 19, so these will be act as these pins are used for generating the clock. Okay, for example, so external, the crystal will be connected to the microprocessor. Okay, crystal will be connected to the microprocessor, and this is, for example, XTAL2 and this will be XTAL1. Okay, so once we connect the crystal to these pins, so internally some circuits will be there. So, okay, together it will generate the clock, so that clock will be used to control the all operations. For example, so each operation we need to do on the particular timings. So if it is in embedded system, basically it is a dependence. First this perform, means this work, then this function, then this function, so like this. So all these things have the particular time, so that all after executing this particular device, this should work. Okay, again this, so like this. So all these things it will be controlled by using the clocks, and microcontroller will work from 1 megahertz to 16 megahertz. Okay, it will work from 1 megahertz to 16 megahertz. Okay, usually the 12 megahertz is most common frequency it will be used, so that will be generated by using the XTL pin and crystal oscillator. Okay, so the next pin number 20 is ground, so which is a necessity for giving the power supply and ground both are required much. Okay, then pin number 21 to 28, so that is port 2. So port 2, if there is no external memory is required, if you are not connecting any external memory, okay, then it will be used as normal inputs outputs. Suppose if you want to connect external memory which is required more than 8 address lines, then this port will be used. So here for this port A8 to A15 are connected. So when it is used for, when external device is connected, external memory is connected, then it will be, this port will be used as a address bus. Okay, so both when it should, it will be used as a address bus, otherwise it will be used as normal input. Okay, this is port 2, and then psen, that is program store enable. Okay, so this is a control signal from the memory. Okay, from the memory it is connected to the microcontroller. So if external ROM is used for storing the program, then logic 0 appears on it every time when the microcontroller reads the byte from memory. So whenever there is a read operation from the microcontroller happens, then this particular bit will be, actually it is active low, and this pin will be becomes low. Once it read means again it is ready for the next read. It doesn't means it means, okay, the microcontroller is ready to, okay, it is ready that to read the next byte. Okay, so that will be indicated by the program store enable. Okay, the next one ALE. So ALE is nothing but address latch enable. This is program store enable and this is address latch enable. So why it will be used is, so port 0, as we know, it will be act as both address and data, that is AD0 to AD7. Okay, so when it will be act as address and when it will be act as a data, as it is a single bus, we call as multiplexed bus. Okay, so why we call as multiplexed is data and address both are multiplexed in a single bus. Okay, so once the microcontroller will put data, for example it has put 12H onto this bus. Okay, after putting this value, if it is generated ALE, and that is address latch enable, if it is, the signal is generated like this, if it is active high. Okay, if it is generated like this, then after this, okay, so once it is generated like this, and it will be act as a what, address. Okay, during this time, okay, when it is ALE 0 to high, during this time it will be act as an address and it will be latched in the register as an address. Okay, so now the same thing here. After receiving the signal from the ALE pin, external latch latches the state of P0 and uses it as a address. So once the ALE becomes to the previous logic state, means 0, again it will be used as data bus. Okay, so whenever the microcontroller will puts data, like for example 12H, and it is generated this signal, during this signal the value will be latched into the register which will act as a address. So once it becomes low, again it will be act as a data. Okay, so this will be the control signal which will differentiate between the address and the data. Okay, so this will be it will be more clear so when we see the waveforms. Okay, so in basically in module 1 we are seeing all the brief introduction about the brief information about the all the module signals, everything. Okay, in rest of the modules you will see in detail, okay, how exactly they will work. So this is ALE signal, and next the P, that is external access. Okay, external access is a input. Okay, so input for the microcontroller, so it will be enabled. Okay, it will be, okay, it will be enabled when we need to use the external memory. Okay, so we need to use external memory. Suppose if you want to use external memory, this pin should be low. If it is active low, then it is we require external memory, means we are interfacing with the external memory. Suppose this pin is 1, then we are not using any external memory if it is active low. Okay, suppose if it is active high, then whenever this pin is 1 we are using external memory, and when this pin is low we are not using the external memory. So this is a pin which will enable or disable the external memory interfacing. Okay, the next one, the last, that is 32 to 39, that is port 0. Okay, so port 0 okay, so yeah, what the previously we have seen, okay, that is ALE. Okay, so ALE is for port 0. Okay, so now the port 0 will have the AD0, means it will act as both multiplexed bus, it will act as address bus and the data bus. Okay, so if external memory is not used, if external memory is not used, so it will be generally it will be used as a, if external any memory is not used, then it will be used as normal input and output. Okay, so when we use the memory, then in that case we need a address. Okay, any external device if you want to communicate with that, so okay, with address, then we need to use the address. In that case we need to give the ALE signal. Okay, here it is there. If the ALE pin is drive high, okay, then it will be act as a address. If it is low, it will act as a data bus. Okay, it is like this. If it is ALE signal is high, it will act as address. When it becomes low, it will act as data. Okay, so whenever the ALE is high, in during that time address will be latched. Okay, because of that we call as address latch enable that control signal. Okay, so port 0 is, it is a multiplexed bus. Okay, so when external device is using, it will be acting as address bus, otherwise normal general input output it will be used. Okay, and the last pin, that is 40th pin, it is a power supply. So 5-volt power supply we will give on to the microcontroller. Okay, so now till now we have seen what are the signals connected to the microcontroller and what is the function of that. Okay, so now actually in the syllabus we have the pin diagram, architecture, all those things. So with that we have some two topics what we are seeing here, RISC and CISC, and also Van Neumann. So in some of the previous question papers in module 1 they have asked these questions. Okay, so differentiate between RISC, CISC and Harvard and Van Neumann. Okay, so because of that I am covering here. Actually it is in syllabus, it is some other module, but we will cover as it has come in the some of the question papers. Okay, so now what is RISC and CISC? So these are the architectures. Okay, RISC means reduced instruction set computer, CISC means complex instruction set computer. Okay, RISC and CISC, reduced instruction set computer, complex instruction set computer. Okay, so these are the designs, these are the architectures which will be using while designing the processor or microcontroller. Okay, so now based on the application we will decide. So here RISC architecture consists of, these are the points. Okay, so what are those? Instruction takes 1 or 2 cycles. Okay, so what you mean by cycle is, so each instruction, so what is the instruction basically? So as we know, the program consists of set of instructions. So as I told, for example, add a comma r2. So what it will do, it will add the contents of a and r2 and result will be stored back to a. So basically add operation. Okay, this is one instruction. So the particular instruction will take less time for execution. So cycle means, so basically what are the instructions are there. So each instruction, for example, addition, multiplication, division, these are some instructions. So each instruction will take some cycles, machine cycle we will call. It may be 2, 1, 3, like that. Okay, so that cycles they are talking about. The meaning of cycles is how much time the instruction will take for execution. Okay, so RISC architecture will take 1 or 2 cycles and CISC architecture will take more cycles, so multiple cycles more than CISC. Then okay, so one only load store instructions used to access the memory. Okay, there are so once we know the once we start the instruction set, then we will come to know what are load instructions, store instructions, all those things. So these load store instructions with respect to the memory. Okay, so only in CISC, only in RISC architecture, only load and store instructions will be used to access the memory, whereas in addition to load store we have some other instructions which will be used to access the memory in CISC. Okay, again here instructions executed by hardware and here instructions executed by the microprogram. Means here the more hardware will be used. Okay, so what are the designs or ALU or whatever it is. Okay, so hardware, more hardware, the design consists of more hardware in the RISC and design consists of the more software in the CISC. Okay, then fixed format instructions, the variable format instructions means, so we are talking about add a comma R2. So finally this instruction we call as assembly level instruction. This instruction finally it is converted into binary format. Okay, so finally it is converted into binary format. Okay, so this binary format it is fixed in the RISC architecture, and this binary format is variable with respect to the instruction in the CISC architecture. Okay, so that is the meaning of that. Then RISC has few addressing modes, it has many addressing modes. So addressing modes are the ways in which the data we can access from the microcontroller. Okay, so there are different ways of access the data. Okay, for example, okay, move a comma 10h and move a comma hash 10h. Okay, here the 10h will act as address. The content of address is accessing from the memory. So hash means directly the 10 value will go to A. Okay, so this is just an example. These we call as a addressing modes. The ways in which we can access the values or data we call as addressing modes. Here CISC has few and RISC has few, and CISC supports more addressing modes. And similarly few instructions and more complex instruction set, and here most have multiple register banks and single register bank. So registers less and here it is more, and pipelined and it is less pipelined. So pipeline is one more the big concept in the sense. So this is the parallel execution. Here the pipeline, here less pipeline means it is not highly pipeline, means very less parallel execution in the CISC, and here it is parallel execution. Okay, so the pipeline is again a concept like we call as fetch, decode, execute and write. Okay, so fetch means read the instruction, decode that, decode means what exactly that instruction, then execute and write the results. Okay, so like that this we call as a pipeline structure, and again here it is FD, EW, and again here it is FD. So when one instruction is decoding, okay, the current, when previous instruction is decoding, the present instruction is fetching. Okay, like this the parallelly it will happen. So this architecture is highly pipelined, and here it is less. And last one, the complexity in the compiler, complexity in the program, means the complexity in the compiler design in the RISC architecture, means the compiler means is the one which will compile the program, which will identify the errors and warnings, all those things. This is a tool. And CISC means it is in the design. Okay, the design is complexity here, and here is the compiler complexity. This is these are the differences between CISC and RISC architecture. Okay, and the next one, Harvard and Van Neumann. Okay, so this basically the Van Neumann means both the program memory and data memory in a single IC, and Harvard means there is a separate data memory and separate the program memory. Okay, so 8051 microcontroller will come into this. Okay, so as we know we have separate data memory and separate instruction memory, so that is 8051 supports the Harvard architecture. So this is also while designing we will use. Okay, so the same thing. So what are the difference between these two architectures? The Van Neumann have the same thing, single memory space for both instruction and data, and here it is separate the program memory and data memory. And as it is a single, okay, it is not possible to fetch instruction and code simultaneously, because only one bus is there, either instruction or data we can access here. But as it is separate data bus and separate data bus for both data and program, so simultaneously we can fetch the data and program here. Okay, and this will take more time, more machine, because only single bus is there, and this will take the less time, so simultaneously it can access. Okay, and use CISC architecture and RISC architecture. Okay, so what we have seen previously now. Okay, the RISC architecture, the CISC architecture and RISC architecture. Okay, and instruction prefetching is a main feature. Okay, So instruction prefetching is a main feature, means so initially we can prefetch, we can before means prefetch is a thing. So we can initially we can fetch all the instructions which will put in a temporary memory, then we can execute. Okay, and here the instruction parallelism means whatever the pipeline what we are talking, so pipeline is more here, as it is a risk architecture, more pipeline and less pipeline. Okay, and also known as control flow or control driven computers and data driven computers. Okay, so the controlling part is more here. Okay, so here controlling part is more, and here it is somewhat less compared to the Van Neumann. And the chip design, okay, simplifies the chip design because of single memory space. And here it is, chip design is somewhat complex because there is a separate memory for data and the program. Okay, the examples for the Van Neumann architecture is, as we are seeing here, 8085, 8086, means that is microprocessor. And here if you see here, uh, okay, this special general purpose microcontrollers and DSP chips, means we can give 8051 example for this Harvard architecture. Okay, so these are the means these are the points in which the Van Neumann and Harvard architecture differs. Okay, so these are the standard questions in the main exams what they will ask with respect to Van Neumann and Harvard architecture and even CISC architectures. Okay, so so today in this session we have seen what is the microcontroller inouts, okay, and what are the functions of each pin, okay, what it will do. Okay, so all these things we have seen, and also with the difference between CISC, RISC and Harvard and Van Neumann. Okay, so in the next session we will see how to interface the microcontroller with the external devices. Okay, what are its features and how to interface all those things. Okay, and some of the, as I told, so some of I referred Kenneth book, second book, and also I have referred some internet resources, okay, with respect to the differences and images. Okay, thank you.